Okay. So first of all, let me thank the organizers for the opportunity to be here and talk about some of the recent work in our group. So I will basically focus on these two works here, and I have changed the order. So I will start with a little bit of spin orbit in two subband quantum. That's the novelty here to some extent, and then I'll show how this can lead to topological phenomena in an ordinary system like 3-5 semiconductors, essentially. So this is it's messed up somehow for. Okay. I don't know, I hope it doesn't really. Okay, so there's some of my collaborators. Some of the students are here. It's impossible. Maybe I can start it again. Yeah, okay. All right, that's better. Yeah. Okay, so the work I'm going to talk about today is essentially done by these people here. John, Poliana, Mark, my former students, and some collaborators from the University of Basel and Iceland. So here's the outline. I'll essentially review a little bit of the spin-orbit interaction. And I allowed myself to throw in a couple very simple slides for the non-expert and for the sake of the students. And then I'll build up on that to talk a little bit about topological insulators, and then show how this kind of system can also sustain some kind of ischemionic densities in real space. So here's some other types of spin-related work in our group. The most recent one is this. We'll flash one slide on this, which we call the stretchable persistent spin helix. And then there's a bunch of other things, all related to spin orbit in the context of topological insulator and other systems as well. So in semiconductors, there's been some renewed interest, that I view it, in spin-orbit interaction due to the recent studies on topological insulators, which are this two-phase solid, if you wish, metal and an insulator at the same time with protected edge states. And in all of this type of physics, spin orbit plays a important role in defining the topology. This will come back. I'll come back to that later on. And also, this has been in 2D. It's been experimentally realized in Molenkamp's group after the predictions. And we have a couple works on that. I will discuss this one today. And of course, the part of this interest comes from the Majorana stuff, which was a major breakthrough in the recent years, especially after realizing that you can generate P-type superconductivity in an ordinary system from S-wave if you have a spin orbit in the system plus Zeeman and so on. And the third reason for that, of course, this is this nice review, which incorporate the works of many of you. I didn't really list the original works here, but we all know that. And then by now well-known result of Copenhagen's group, where you have this zero bias peak and this kind of configurations. And a last point, which is quite interesting as well, is this emergent fields, emergent gauge fields, and synthetic gauge fields, if you wish, in the context of cold atoms and optical lattice. So these three sort of topics made spin orbit research again after, in the last couple 10 years. So here's my one slide on the idea of spin orbit interaction. From the atomic physics, we have the usual argument where you sit on the electron and the nucleus goes around, and the electrons having a spin, it fills the magnetic field generated by this loop of current. And that is essentially what the origin of the spin orbit is. It's mu dot B, and B is essentially the field that you get by changing coordinates from the from the nucleus to the electron. So you essentially get this kind of form of the Hamiltonian. When you write the corresponding Hamiltonian, you get the usual textbook expression. You're used to writing it in terms of the LS coupling. Now you can go through the same kind of argument in a heterostructure. So here you have for the hydrogen atom, for instance, this is just a gradient of the potential, the Coulomb potential. In a heterostructure, V is essentially the heterojunction potential. Could be a quantum well, it could be anything. And the crucial difference is that essentially if you're a 2-DAG, like I illustrate here, the electric field is essentially perpendicular to the interface. And moreover, you can actually, by just, if it's just a Z direction there, when you plug it in this formula here, only the Z components survive, and that gives you the so-called Rajba Hamiltonian. So that's the very famous Hamiltonian back in the 60s in a different context. And the crucial and interesting part here is that the strength of the spin-orbital interaction is now gate controllable. So if you apply a gate to the structure, you can actually change this alpha here electrically, right? As opposed to the atomic physics in which you're sort of stuck with what you have in the atom. Now, all this is sort of old stuff, and it was part of the interest in the quantum spintronics was to control the spin via this kind of interaction. Can show that this Hamiltonian I just flashed to you, it can be used to manipulate, to rotate the spin of an electron, and you can come up with things like this so-called data dust transistor, which was proposed in the early 90s, and just recently it was realized experimentally. So you can actually find modulations by changing this alpha constant with gate. You control the rotation in this two-terminal geometry. But of course, this is all very simple. To actually understand the spin-orbital interaction, you have to go do a bit more work and actually consider the K dot P framework. And for that, say we have a quantum well like this. Gallium arsenide could be anything. The same concept will also apply to the Wurtzite system. I'm mostly focusing on zinc blend structure here. So we have all these parameters that describe the offsets of the wells and the heavy holes and the light holes and so on. You can, in principle, construct, if you have, if your student have interest in discussing how you derive this, you can go to the site I mentioned. You can construct a Hamiltonian like this. That's the simplest so-called Kane model from 1957. It has this whole sector here of the hole, which is not really entirely correct because I have a bunch of zeros here, but that's not relevant for us because we're really going to be interested in the electron sector, and for the linear in K spin-orbital interaction, that Hamiltonian is good enough. You can also construct Hamiltonian just like that for Wurtzite system and do the same kind of derivation I'm going to outline next, which is the proper way to address spin-orbital interaction in the system. And this could be done for a quantum wire, a quantum dot, or a quantum well, as I will illustrate next. So the form of the potential enter in the diagonal there. Now, that Hamiltonian I just showed you has this form, and I can, if I want to focus on the electron sector as opposed to the whole sector, I can essentially use linear algebra and rewrite this as a two-coupled set of equations and then do some substitutions there and end up with a Hamiltonian like this here. Not really a Hamiltonian, not really a Schrödinger equation in the sense that we know, because the energy that appears here is also in the Hamiltonian. But it turns out that when you properly expand this in the order of the inverse of the gap, and you renormalize the wave function accordingly, you end up with an effective Schrödinger equation without energy there. So this you can do when it's done actually in many books. So this is the Hamiltonian I just showed you before, written in a more compact way. And now I can calculate this HP tilde, which is the effective Hamiltonian for the electron sector after I eliminate the whole sector. So that's like a Schrieffer-Wolff transformation, if you want. And you can do that, and you end up with this kind of Hamiltonian. So you have here a kinetic term, and then the potential would be the Hartree potential, the heterostructure potential, and then you have these three terms which I separately wrote like that, and they are the spin orbit terms, right? And then you have additional terms that could give rise to things like the Darwin term and so on, which I will not worry about. But that's an effective 2x2 Hamiltonian for an electron, right? In principle, you can do the same thing, done the same thing also for Wurtzite systems. I'm emphasizing this because there's a lot of interest in Wurtzite system these days. So I can define this alpha H, which is, I call it Hartree contribution to the spin orbit. And this is gate plus doping, and this is just the structure of the offsets of the well. So there are three contributions. And this is very similar to what you can do the same kind of procedure, of course, if you have a Dirac equation. So you have a Dirac equation, you apply this sort of folding down technique, and I can derive a Pauli matrix if you wish. That's how you properly derive the spin-orbit interaction in the Schrödinger equation, right? So by starting out from the Dirac equation with the external potential, you can derive things like that, and then you see the spin orbit there, which is the equivalent of the one I just showed you. And then there's things like the Darwin term and the mass velocity and so on, right? So back to this, I go now make some approximation to move on, and so I can show this is very small, and moreover it's independent of spin. So I just forget about that for now, and I regroup the three terms I had in terms of this Hartree gate plus doping plus the structural part of the spin-orbit interaction. So this is the so-called Rajba Hamiltonian. That's the sort of K dot P derivation of it. It's the more grown-up version of the atomic physics argument I just gave you. The bonus of doing it this way is that in principle you can calculate alpha, and that's what I'll do next. So I have this 2x2 Hamiltonian. One way to solve it is to solve it numerically if you want, but a perturbative way is to project this into the lowest eigenstate of the system, meaning that I neglect the off-diagonal term. I just solve the system with just one subband, and I can project that Hamiltonian again in this lowest state. So that's the Rajba Hamiltonian. And in the process, you actually find out what alpha really is. So this is something you can calculate. We have extensively done some calculation, numerical calculations to determine these constants in these papers here. And that's the usual Rajba constant, or Rajba coupling, if you wish. Now, a couple of years ago, we extended this procedure to consider two states in the well. And then, of course, it's a natural thing to do. And you end up with two Rajba constants now, alpha 1 and alpha 2. So you have the two of those sectors. But in addition, you have a term that couples the two sectors. And of course, here the constants, and this is the intersubband coupling. And the interesting thing is that this coupling here is non-zero even in symmetric structures, where you have no Rajba spin-orbit interaction. So that's the case I'm going to do next. Before I move on, just to, as a way to show that this approach works very nicely, we have a recent collaboration with the Basel group, the Dominic Zumbel, with samples from David Ashelam, where we performed, as my postdoc at that time, performed all this simulation. We calculate all these alphas, and we're looking at the matching of the alpha equals beta, the alpha equals beta symmetry. So that's a symmetry that gives the so-called persistent spin helix, which I will discuss in a bit. And so the same kind of description I used in this work was done here, so it sort of lends some support to these ideas. And then what was done in this paper here is that we were able to show experimentally using weak localization, weak anti-localization as a detector for this alpha equals beta symmetry point. We show that it's possible to lock the Dresselhaus and the Rajba over a wide range of gate voltages. So it's not just a single point anymore, but rather a range of values here. And in this case, you can essentially stretch the sort of persistent spin helix between these 2 points here. So back to the two subband Rajba models. So I have this 2x2 model, and you can actually solve this, calculate the dispersions. You have this anti-crossings because the bands can cross, and of course because of eta, the anti-cross. You have 2 Dirac cones, so that's the usual model. This kind of physics has also been seen in this kind of systems where they see these two subbands, right, in the metallic system, and then they have this anti-cross in there. So in this experimental work, they actually measure this delta here is essentially the energy associated with the intersubband coupling. Of course, it's a metallic system. It's a much bigger energy scale here for the spin orbit for alphas. For instance, alpha 1 and alpha 2 here, it's like 300 millielectron volts. It's the same kind of idea. Now, let me just do the fully symmetric case. So I have a 4x4 system which describes a anomal with 2 subbands with alpha 1 in the first sector and an alpha 2 in the second one. And I'm going to consider the fully symmetric. That means that alpha 1 is 0 and alpha 2 is 0, but eta, the intersubband coupling, is non-zero. So the Hamiltonian now looks like this. And so I have a kind of Rajba spin-orbit interaction in a symmetric system. It's just non-zero because of parity. So eta is non-zero, right? So in this Spanish language, you can write it like that, including, you can define some pseudo-spin if you want, and you can solve this problem, quite simply, analytically, and of course, that's the dispersion I just showed you before, so it's not gapped, right? It's still metallic if you want. Now, within this framework, what can we do with that? Well, first of all, maybe later today, Guzev is here, is one of my colleagues at the University of São Paulo. This is 2 years ago. They measured this spin Hall effect, spin accumulation in 2 subband symmetric quantum well. I'm just going to flash this because we used the same model I just described recently together with Sasha Kayatsky, a collaborator from previous years, to actually explain many of the features in this kind of experiment. So you may remember from the old times in this spin Hall business, a Rajba spin orbit interaction does not really generate any spin Hall effect. It's 0. It's linear in K. But in 2 subbands, that's what the São Paulo group found. So it's an interesting finding. You can see in the archives the theoretical discussion about that. Now, how can you make this kind of system topological? So I showed you just trivial thing, right? 2 4x4 system with the spin orbit. Now, just a reminder of the ingredients, the relevant ingredients for a topological phase, a topological insulator phase. So you need a system which is a bulk insulator, and then you have to have a knob somehow to turn and make the gap close, essentially invert the gap, right? And some residual interaction will, again, split the bands after they cross, and you end up with another bulk insulator. So it's a bulk insulator before and after the crossing. So the gap has to close. And as we learned yesterday, Professor Du mentioned experimentally some systems where they have this behavior. So the checklist essentially is what I just said here. You can also calculate, to go from this to that set of states, you have to somehow close the gap. So you're changing, if you want, the nature of the system. It's like a phase transition, not the conventional one, characterized by some topological invariant that you can calculate. And of course, then this is all bulk, right? So it's bulk. It has a topological invariant, and then you can eventually cut the system, make it finite, and the consequence is that if it's topological, the edges will have the physical edges of the system will sustain edge states. There will be quantum states solutions, quantum solutions of the Schrodinger equation of the system that live on the edge. So that's what it is. And they're helical and so on. So you need this kind of ingredient. You have to be able to make the system, or you have to be able to synthesize a system that obeys this kind of, have this kind of ingredient, and then you would have a topological insulator. Now, you may remember the so-called BHC model, the Bernavig, Hughes, Zhang model. It's a 4x4 system, right? It has a whole sector and an electron sector. They are coupled, but it's a 4x4 system. Now, I just showed you a Hamiltonian, which is 4x4. But of course, ours is not gapped. The BHC is gapped. You have two bands. It's very much like a Dirac equation solution, right? Where you have the electron sector, positive energy, and the positron section, if you want, the electrons with negative energy. So if you're able to change M0 to minus M0, in principle, you could have an inversion also in the Dirac equation. So the Hamiltonian I showed you before is 4x4, and that's the Hamiltonian I'm going to now try to play with a little bit to get this kind of behavior. So there are some related works, and the motivation for that is essentially that most of these 2D topological insulators, they are mercury telluride, from the mercury telluride family. And that's done basically in two groups I know. One is Monenkamp's group, and the other one is Novossibsk's group in collaboration with Gusev. And people are trying to get this kind of topological insulator behavior in more simpler systems. And yesterday we had a nice talk by Professor Du where they showed some experiments involved 3-5 materials, but they still have electrons and holes, right? And it was following a proposal in Zhang's group, Zhang's group in Stanford. And there are, of course, other additional proposals, and all of them essentially use electrons and holes. So what we're going to try to do now is to just use electrons and in an ordinary system. So what we do is, this is again the same system I showed you before. It's in a double well, so I have two subbands, right? But of course, this system doesn't work. I mean, it has this kind of Hamiltonian. I just rewrote it in terms of this parameter here, which is the energy separation of the two confined states, delta SAS, right? Of course, if you solve this is what I showed you before. I just rotated the basis so it looks like it's two blocks. Right? It's exactly the same Hamiltonian I had before. I just rewrote it using this parameters now. So it looks like, if you know the BHC model, it looks like the BHC model. The BHC model is a 4x4 model with two blocks like that. And the BHC model can have a phase transition which is topological. So what do we do? How can we actually make this model topological? So this is the 2x2 block, one of them, for instance. So one thing you can do to open up, we essentially need to open up a gap. We have to have two bands essentially that cross and then have a gap. So what we propose is to add some modulation on top of the 2DAG, essentially a super lattice. You can actually make pits. People can do that experimentally. For instance, I'm representing this kind of lattice here on top with this kind of potential. And it turns out that it generates potential like that. If you just plot that using MAPE, you see that this generates some modulation in the 2DAG, which is sitting below here. I mean, we actually have done the Poisson type equation to understand how the potential goes. So it's essentially constant and modulated like that in the plane, right? It's an infinite system in the plane. And of course, then you can just take this Hamiltonian, which is the one block, for instance. You do this for two blocks, of course. So you take this and you add this periodicity, and then you can solve for this, right? You can solve it. We did it in the paper numerically, but we also did it using the nearly free electron model. Essentially analytically, you can understand it very, very simply by using the nearly free electron model. So this is a part of the band structure of the system along this direction here, in the Brillouin zone. I'll show you the full band in a bit. But the two bands that cross are essentially this one here and this one. And I have to manage to open a gap here. And this gap has to be an overall gap, right? So way to understand that, and that what will give me the gap will be the eta, the inter-subband coupling. That's what will open up a little gap there. Now, to understand this in sort of a 101 solid-state physics class, we all drew this kind of spaghetti diagram for like free electrons, right? So you can see that you have the usual bands. We've seen this yesterday. Someone showed flashed band structure in 1D. So you have the usual bands here for one well, right? That's a pictorial way to look at it. And you have the same thing for the other well, shifted by delta SAS. So the first subband here on the other well, which would be the equivalent of this one, actually overlaps, if you want, with that one for the first well. That's how they get the inversion. The nice thing is that delta SAS is tunable. In principle, you can change the heterostructure, but you can also apply a gate, and the gate also changes that. So you can go from topological to non-topological. That's what I'm going to show you next. And if you zoom in there, of course, you have the Bragg reflection that is neglected in this kind of diagram here. When you put the Bragg refractions, you get the opening of gaps here and in other directions of the Brillouin zone. And when you include now, do the full thing, that's the diagram you get, right? So the two bands I was talking about is this one. You can see it's an overall gap through the whole of the Brillouin zone. And it's a tunable gap. I can change this M, this so-called, in the language of this BHZ model, that's what we call the mass gap. It's essentially in that language the difference between E1 and H1, the heavy hole, and the electron, the first electron level. And of course, in our system, we can do that by changing delta S, SAS, but also the potential V1 and V2 that characterizes these superlattices. So that's a gate on top of the system that can change these parameters, and you can actually tune from a positive mass gap to negative mass gap. And so you can have an overall gap here. So this is the topological band structure. If you go to the next slide, that's the non-topological, non-inverted regime when M is 0.1. So you see, again, it's an overall gap. It's tiny. That's why the referee complained. He said, well, can you make it? It's like, if you optimize our parameters, you can get maybe 2 millielectron volts. That's like, I don't know, 0.5 millielectron. This is tiny, right? There's all the other gaps in 2D. And he said, well, if you can make it at room temperature, then I accept it in PRL. Well, if we could make it at room temperature, we would not send it to PRL. Anyways, you can go on and you calculate topological indices, and you can, this churn number, you can see it can change. We can, have this phase transition at some gate value there. So what about this bulk edge correspondence? This is all bulk so far. Now, I can make a strip of width D here, right? And I can actually solve the system in a non-inverted and inverted configuration. So for the non-inverted situation, now I quantize the system, I confine it, so I get the subbands, right? No edge state, so just the bulk, subbands of the wire. And of course, if you now tune the system so it goes into the topological phase, you get the usual edge states with some curvature and so on, right? You can plot, of course, the edge states, in the wave function of the edge state, you can see some oscillation, you can fit within the BHZ model. We can actually construct a BHZ model from a nearly free electron description. It's all the parameters are very, very, in the appendix of the paper, if you're a student, you're trying to learn, it's very instructive because it's all done. We did it numerically, but we also did it using the nearly free electron model. It's in a very textbook. So you can understand all the parameters, and you can actually try to optimize the system parameters so you can get what you want. So let me move on now to the second part, which is going to be essentially a regime where we can try to find the Skyrmions in the system. So now I'm going to go in a regime where I don't consider eta at all. So I have a 4x4 system, so I'm resetting the problem. I have alpha 1, alpha 2 in the two subbands, and I also have the Dresselhaus term in one band and the Dresselhaus term in the other band. Well, we'll neglect the inter-subband. I can do that because I can tune my Fermi level. And as a matter of fact, for gallium arsenide, this is irrelevant, this inter-subband coupling. I can always be away from it. So I will essentially consider a case where I have two decoupled subspaces, subband 1 and subband 2. Right? So this is the Hamiltonian, if you're curious to see the derivation. So what we do here is what I outlined previously, but including also the Dresselhaus. It's in a supplementary material of our recent work. So this is the full description, has the cubic Dresselhaus. So we renormalize the linear Dresselhaus term and so on. So for now, I will essentially neglect all these interband couplings here, and I have one block and the other block, 2 by 2 blocks, right? So where I'm going with this? Well, if you had just one block, that's an old work that we had in which we found the symmetry. Alpha can be tuned electrically. So you can tune it so that it can match beta. And when you do that, what you find is a conservation law in the system. You can show that this capital sigma here commutes with the Hamiltonian of the system, even in the presence of disorder there. So spin, if you want, in this sense, this combination of spin is conserved. Right? So that's one particular point. That's why this other paper that I mentioned before, the stretchable persistent spin helix, is interesting because we actually now are able to show that you can tune this dynamically. You can change alpha and beta at the same time over a range. So you get, from this, you can solve this problem exactly like this, even in the presence of disorder, small disorder. And you show that the wave functions acquire phase, essentially, right? So with that, you can, at that time, we call this the non-ballistic spin field effect transistor. That means that the spin is protected because the internal electric field, another way to view it, is to look at this Hamiltonian in terms of an effective magnetic field. I'm just dropping the disordered potential here for the sake of the argument here, but the spin-orbital interaction can be viewed like this, and I rotated the axis so you can explicitly see what happens when I have alpha equals beta, for instance. The field becomes unidirectional along this particular direction, and I can do the same. And then, of course, then you suppress the Equinopera and the Elliott-Effet type processes when alpha is equal to beta, and you can do the same thing if alpha is equals to minus beta, right? So from that, I can essentially construct a spin density if I have one subband only going into this basis, frame of reference here. I can write the Hamiltonian like this, and I can exponentiate this, and this is like a gauge transformation. And I can immediately calculate what is the effect of the Roswell-Dresselhaus Hamiltonian on a spin-up, for instance. And I get this kind of spinner from which I can calculate a spin density. And that is the so-called persistent spin helix. And, this does not change in time if you neglect or if the cubic terms are, cubic Dresselhaus term is small. And of course, this has been realized experimentally. Another twist was added by this nice paper by Andre Berneweg and Hornstein and Xu Zhang, in which they construct an SU2 type symmetry. What I just showed you was like a U1 symmetry, one axis. Now you can actually construct a SU2 type set of operators in terms of this capital Q here, which is essentially the spin orbit at alpha equals beta. This is valid for alpha equals beta. And you can show, and this is a nice result actually, that even if you put in electron-electron interaction, which we didn't have before, you can still get these quantities are conserved essentially. And then of course you can come up with what they termed this persistent spin helix, PSH. Now, this has been verified experimentally. You can create this kind of densities with this so-called transient grating spectroscopy. So you can generate densities like this, which is essentially a sum of those two. And they do measurements, time-dependent measurements. You can go through this and find short-lived and long-lived excitations. The long-lived ones are the PSH. And they can tune the angle between the lasers and actually select the Qs and eventually see a big peak here where the decay is small. That means you attain the PSH regime. So that has been experimentally verified, and the Zurich group also has imaged this kind of excitation as well. Now, what can we do when we have two subbands? What we can do with two subbands in gallium arsenide this is all realistic parameters now. Two subbands, I can calculate all the alpha 1, alpha 2, and so on. And you can, in principle, have the system tuned so that you match this kind of condition for the first subband. And I can do alpha for the second subband. I have the opposite sign now. This is the new thing here. And of course, this comes from the calculation. We calculate alpha 1, alpha 2, and beta 1 and beta 2. And here, for the first subband, I can have alpha 1 equals beta 1, and alpha 2 equals minus beta 2. I said, why is this interesting? Well, it's interesting because you can, in principle, these Fermi cones or the Fermi circles are like orthogonal, if you want. And that means you can generate PSHs that are orthogonal. I can go for the same kind of argument I just gave you before. So I can generate a wave like this for the first subband and a wave like that for the second subband. They're both robust. They both preserve the symmetry. And this is the spin density there. We actually did the whole calculation with Keldysh and stuff to calculate the densities. And you end up with this kind of spin density for the lower subband, the second subband, and you can add the two. And this is a topological density, in fact. In what we just did here, I mean, you can actually make a nicer plot, 3D plot. What we actually did here was we found a way to realize a spin density that was actually proposed many years ago by Benson Vishwanath in chiromagnets. So there, chiromagnet, you have this magnetization. For instance, this one, they call it a spin crystal. So this is exactly what we have there. So if you plot this, you can define a Skyrmion density, a Skyrmion number, and so on. You can calculate, and of course, because of symmetry, if you calculate the Skyrmion number is 0, but then you apply a magnetic field slightly up or down, and you can see the magnetization jump. So it's quantized. So this is actually a realization of that. And why is this interesting? Well, in all this chiromagnet business, in a month from now, we're starting a program here, advertise it a little bit, which will all have many of these talks on Skyrmion stuff. So people are interested in the so-called topological Hall effect. That means that, you've heard the word emergent gauge fields a couple of times today, and in the chiromagnets, when you inject an electron, the electron sees this texture, and because of it exchange coupled to this magnetization, it follows this adiabatically, and it feels an effective Lorentz force, which actually can be opposite to the usual Lorentz force. So you add some blips to the signals you're measuring. So this is called topological Hall effect. But there's also something called the Skyrmion Hall effect. You can actually make the lattice drift in the presence of a magnetic field. And because of Faraday induction law, you end up with a time-dependent electric field. We just heard about that in the previous talk. So this emergent electric field acts on the lattice, the whole lattice, and it drifts sideways. That's so-called a Skyrmion Hall effect. So in principle, I'm actually running out of time here, but in principle, you can, dream of doing this kind of thing in ordinary materials. And this has been, for instance, this PSH, with just one PSH, you can electrically drag it. And in principle, you can do the same here. And hopefully, look at some of these topological effects in ordinary gallium arsenide system. So I'll end with this one. So this is in a month from now. So if you're here already, you can either stay on with me. I'm staying here for 4 months. This is my sabbatical. Well, you're welcome to stop by my office to discuss many of interesting things we have been doing. And a bunch of I didn't have time to talk about Majorana fermions. We have a couple of interesting results as well. So feel free to stop by. Thank you.